Attention class, this is Dr. Barnes, and as a result of doing today's tutoring session, I'm actually going to recreate what I went over and sit back and create and give you guys what I'm going to call the Reese's Cup lecture, just because it really helps us, in my mind, relate in the understanding of the standard deviation to a level that we could not have done when we first introduced the concept of the standard deviation, right? And again, I say this all the time in class. We talk about how math is fundamental. It builds on each other. And quite frankly, this goes to show how a concept that we talked about early on, we were talking about different types of statistics, but then we got deep into it in unit 3.2, is still relevant to the discussions that we're doing throughout chapter 6. Now, to make it real, what I ended up did is I went back and I looked at the data that we actually have from this class. This is actually a screenshot of the textbook that I used. And what I'm going to do is this. I want to get a true image of the diversity that exists in this class. So the real students' grades, of course, you can't see their names, that I'm going to be looking at for this example is this right here. These 4 grades. We got an 82, 40, a 94, and a 54. Now, you might remember this Excel spreadsheet, which we went and did in class. I entered in the 4 values that we're going to be using directly into this document. I mentioned before, this is something that can be done with any value. So the scores we looked at were the 82, the 40, the 94, and the 54. I rounded them just to make things more simple. Now, I keep talking about how we have to make sure that we understand the notation. The most important thing for this notation right here is that we understand what X is. X is what we refer to as an array. And the values in that array are these right here. The first value is 82. The second one is 40. The third one is 94. And the fourth one is 54. So X is an array, and these are the values in that array. Now, the most important thing, which we're going to be talking about a little bit later, is calculating the mean. Now, you guys know you can do this on your own, but if you were to calculate and add these values up and divide them by 4, that would give you the mean. And you can test me, call me out if I'm wrong. That value is going to be 67.5. So calculating the mean is easy. You can do it. You have it right there. Now, keep talking about the importance of stressing and understanding the notation. I call it alien, but this is what makes us a stats nerd, right? What we need to do is to make sure that we understand what this is asking of us. Even though it's not saying it in English, what it's saying is you take this array and you're going to square the values in that array. So we're going to take 82 and we're going to square it and put that value here. We're going to take 40, square it, put that value here, 94, square it, so forth and so on. Now, I'm not sure if you guys can see it, but I actually already have these values being calculated. And those values are already here. I would encourage you to pause if you're having a difficult time understanding it, right? Just to make sure that you get it. I want to make sure that you guys know how to square these values. The easiest one to probably see with the naked eye is 40. And that's because we know that 4 squared is 16, right? So 40 squared is 1600, right? Now, what else is this notation of alien telling us? One of the first things it says up here is summation. Now, this right here is another example of alien. This means sum. So when you see this equation right here, we've talked about this before, this means the sum. Essentially, to get the sum, what we would do is we would sit back and we would take all these values right here and we would add them up. Now you can do this on your own, but I'm going to save the time just a little bit. If we add up those values, the value that we would get would be this right here, 270. And that's because we have to understand what this is saying. Sum of X. The sum of X, which this array, means you're adding those up, you're going to get a value of 270. Now, I also told you what X squared equals, right? Now let's look over at this table. What does the sum of X squared refer to? That's this right here. The sum, we're going to add up these values right here. We're going to add up all these and add them up. When we add those up, that's going to give us the sum of X squared, which we have listed right here. We're just adding those values up. Now, again, you can pause the video if you want, but I'm going to just sit back and reveal, if you can't see it already, what those values are. When you sum them all up, you're going to get a value of 20,076. Now, keep telling you, we go deep. No, I'm upsetting a couple of people by using things like alien and the notation and making us attend to all the details. But look at what this notation is saying. This notation is saying we're taking X, which we know is not one value, it's an entire array, and we're going to subtract it by X bar. X bar, again, more information proving that we are a stats nerd. X bar is referring to the mean. We already talked about that being a value of 67.5. Now, for this, what we're going to do is we're going to take X, which is 82. We're going to take our 82, and we're going to subtract it from our mean, which is 67.5. Now, when we do that, we're going to get the values in this cell. For this first one, the value, if you can't see it, is 14.5. Now, since X is an array, for this value, we would take 40. We would take 40 and subtract it by 67.5. For here, we would take 94 and subtract it by 67.5. And for this value, we would take 54 and subtract it by 67.5. When we do that, we get these particular values. Now, what I want to show you is what's really going to refer to this as being the Reese lecture. Is the fact of looking at this. Now, here's the thing. You guys have seen this now, but we weren't familiar with this when we first talked about the standard deviation earlier in the semester. We know how to draw a normal distribution now. And I think everybody knows that in the middle of the normal distribution is the standard deviation. That is the 67.5 that we were just referring to in all our previous problems. What I want to show all of you is how this works. This is going to be a value of 65. This is 60, 55, 50, 45, then a value of 40. So this really should go further out. And then this is 65. This right here would be 70, value of 80, 85, 90, and then let's say 95 is right here. Now, what I want to show you is how each of these values in this original array are represented and how they relate to the mean. Each of these values. So what I'm going to do is I'm going to put them on this chart. The first value is 82. So this is 65, 70, 75, 80. 82 would probably be right here. We're going to make that red. The next value we have is 40. That's going to go all the way down here, and it's going to be right on this line. The next value that we're going to have on here is 94, I'm sorry. 70, 75, 80, 85, 90. Right? That would be kind of right here, just shy of the next one. And then our last value is 54. And we're going to make that orange, which would be 65, 60, 55. So 54 would be right here. Now, what I want to show you is how this works. If we were to look at the score, because you got to understand, I made you guys calculate this, but somebody might have been like, why are we calculating this? This is like dumb. This is taking this value of 14.5. I want to show you what it looks like and what it means. The value of 82 is the value that we have right here. When we look at where 82 is from the mean, it is 14.5 values away from the mean. 5, 10 plus that's 14.5 spaces away from the mean. That's what that value is referring to. The next value is 40, which is the purple. If we were to look at this 40, you can count it if you want to, right? But this is negative 27 places away from the mean. Our next value is the 94. If we look at that, that is actually 26 spaces above the mean. And then you look at the 54, that right here is negative 13.5 spaces or 13.5 spaces below the mean. What I want to show both of you is this, and this is something that we have it. If we sit back and add up the positive deviations and we add up the negative deviations, something's going to happen. When we sit back there and we look at the negative deviations are negative 27.5 plus negative 13.5. And then our positive deviations are 14.5, 0.5, and then 26.5. When you add these two values up, these deviations that are below the mean are going to cancel out with the deviations that are above the mean. You add the ones that are below, it doesn't matter. These values could be anything. I picked 4 items at random that were from the class of this semester. However, they can be in any scores. It is a fact that since the mean is defined by all 4 values, and the mean is right dead smack in the middle, that the scores that define this mean, they are deviating a certain extent from that mean. And it'll be a fact that the sum of those deviations will always equal 0. So on the sum of the negative deviations will equal negative 41, and the positive deviations will be 41. They can actually be an unequal number, right? These numbers are, actually they are pretty similar, right? But the deviations, when you do the negatives plus the positive deviations, they will always sum out to 0. Now, if you guys remember this activity, we talked about that. We talked about how one of the processes that we use to make sure that you're not making a mistake is to look at the sum of the deviations in the problem. We already did that. Now, we're going to alien, just like we said before. We need to understand what this is referring to. This is the sum. That's what the sigma refers to. The sum of x minus x bar. That's essentially giving us the sum of these values, which we just plotted on the normal distribution that we have. So we're going to add these up. And just like we showed on the previous slide, when we add those values up, they should equal 0. And that is why I said, when you go back and watch that video, if you do, this is a great place to look to make sure that you haven't made a mistake. because the sum of these deviations, if you did it right, should equal 0. It's just a fact about how the mean absolutely works. Now, also to understand this standard deviation, we want to understand this notation right here. So what are we saying here? Now, if you remember from algebra from high school or middle school, they might tell you that you always work within the parentheses first. So we're going to get x minus x bar. When we get that value, we're going to square it. That's the same thing as taking each of these values and just squaring it. And when we do that, I'm going to make it just in case you are unable to see it. It's pretty faint on my screen. But those values are listed right here. Now, again, understanding alien. This right here, we have the summation. First thing we're talking about. This is adding up all the deviations that x minus x bar that we squared. So again, we're taking these values right here, adding them all up. And when we add these values all up, that's when we get this value right here. And that value, just in case you can't see it, that value is 1,851. 1,851. All right, now I'm going to leave from here and go to the handout that we also did and we went over in class. Get rid of all these drawings so it's out of our way. Now, we followed through all these steps on the other spreadsheet. What we're going to do, you got to remember that this value that we're talking about is 1,851. Hope I got that right. Now, when you're calculating the standard deviation, this is the equation that we're looking at. Please attend to this value right here is this portion of the equation. It's the numerator. So if we're going to calculate S, we're just going to plug those values in. We got the square root. We got the 1,851 divided by N. Now, guys, I'm going to go over this quickly, but N and capital N are two things that we've talked about several times in class. This is the importance of the details that I keep trying to stress. I know it kind of frustrates some of us, right? But we need to know these things because statistics is fundamental and it builds on previous knowledge. Lowercase n stands for the sample size. The sample in our mean that we calculated was 4. So we're going to sit back and use this right here. It's going to be 4 minus 1. Now, I fast forwarded and went through the baby steps. But what we're doing right here is we're taking these baby steps. Again, the first baby step is the 4 minus 1. We got the 3 right here. The next baby step is to divide the numerator, gives you 617. We can't forget to take the square root, which gives us 24.839. And then we round. And since the 9, which is the last digit, is greater than 5, we round up to 24.84. So S, our standard deviation, a lot of calculating that we did right here, right? That is 24.84. Now, that's how we calculate the standard deviation by hand. Why do we do that? Why is this important? This is very relevant to much of what we've been doing lately. When we sit back and have our normal distribution, I think we all know what value is right dead smack in the middle, which is the mean of 67.5 from earlier. 67.5. Right? The mean is always in the middle of the standard normal distribution. Now we just calculate this one standard deviation. That's S. S equals 24.84. Now, you might still be asking, like, okay, I kind of knew all that. But let's sit back there and think about what we're learning as of late. Just recently in class, we talked about the empirical rule. The empirical rule stated that since this information is normally distributed like this, we can use this information to learn about the percentage of scores. You remember in class, it's a fact. This is always the case since this data is normally distributed. In between the standard deviations, one standard deviation above and one standard deviation below, in between this area rests 68% of the scores. 68% of the scores. That's what the empirical rule talks about. In this red region, one standard deviation above and below the mean, 68% of the scores. It also goes so far as to sit back and talk about what exists two standard deviations above and below the mean. Two standard deviations above and below the mean, which would be all of this area, including the red area, this region right there, rest, text, 95% of the scores. So from this area all the way over here rests 95% of the scores. And it's upwards of about 90% if we were to go so far as to look at upwards of 99% if we were to do 3 standard deviations above the score. Now, here's another thing. Let's sit back and look at this. So that's what the empirical rule is saying. With the normal distribution, when you find out the standard deviation, when you look at this is how you can know what percent of scores fall in between there. And the fact that this is a fact, 68% fall in there, the same logic of whether this is a fact is exactly why we also use the standard table in the back of the book, which we've been using across every unit for the last couple of weeks. That's because when the data is normally distributed, we know it behaves a certain way, and we know that scores fall a certain place around the mean. Now, how can this be important? If we look at this right here, 95% of the scores fall within 2 standard deviations. Now let's sit back and focus on what percent of the score are outside of 2 standard deviations. So we're talking about this region right here, and then we're talking about this region right here. If you might remember, the textbook went and argued and talked about how if values are 2 standard deviations above the mean, we say it's significantly high. If a score is 2 standard deviations below the mean, we say it's significantly low. Why do we say that? It's because the data is normally distributed. It's because the empirical rule, 95% of the scores fall within 2 standard deviations, right? So if there's a 95% chance that scores fall within this region, something that's beyond that region, that's significant, that's unique, that's unlikely. So we'll say it's significantly high, or we will say it is significantly low. Now, let me tell you one other thing, and this is also relevant to the homeworks that are creeping all the way up to what we're doing right now. When you know these values, we know that the mean is 67.5, and we know that one standard deviation is 24.84. Not only do we know that where the cutoff is significantly high or significantly low, we can calculate those values. And I'm going to show you how right now. Now I went ahead and calculated these values, but as you can see, since we know the cutoff of 2 standard deviations above the mean is significantly high, and in this situation, we actually know the value of the mean, which is 67.5, which we have highlighted down here at the bottom of the page. We can calculate the value which is here. We can calculate the value the actual value that's 1 standard deviation above. And that information is listed here. We take the mean, we add the standard deviation to it once, we get a value of 92.34. That's the real world value of that. Now, just like some of the homework problems that we've done before, we can find out the cutoff for what's significantly high as well. 67.5 plus 1 standard deviation plus another standard deviation gives us the cutoff right before it becomes significantly high. Right before it becomes significantly high, right here. That value is 117.18. We can do the same thing on the negative values. 67.5 minus, and then 67.5 minus that value twice. So right before it becomes significantly low, that value is 17.82. Now, when I sit back and think about the standard deviation, this is a complete understanding of what the standard deviation is and how it relates to almost everything that we are doing throughout this unit. As you guys can imagine, when we first did this in section 3.2, there are so many things that we did not know and understand. But again, I mentioned before how math is fundamental and it builds on top of itself. So if you remember and pay attention, what we see here is that the standard deviation was built on and made even more important and relevant when we talked about the empirical rule. It was built upon and made more relevant when we talked about a normal distribution. It was built upon and made more relevant when we talked about z-scores and how the standard normal distribution and things work. The details that we're trying to relay are relevant. They build on each other. And I think, honestly, this is the best and most complete understanding of the value of the standard deviation and why we're doing it that we could not have done day one. If we talked about this on day one, there would have been so many questions about what is this, what is that, what is significant high, what is the 68%, et cetera, et cetera. But as you can see, it builds upon itself. I want to thank Reese Cup for allowing me to sit back and have this lecture because it was an aha moment that I had. I hope this is useful for all of you. Good night.